Good morning, thermodynamics.
Hello.
Hello, Bryce and Nicholas.
Hello.
Let's see who else I got here. Oh, we got a good group. We got Alex, Nicholas, Dawson, Bryce. Got a good group.
Professor,
Yeah.
I was wondering if you could do question, what is it? Question 38 from
Yeah,
last week's homework.
I'd love to. Let me find it. No, we're talking to Bryce, right?
Nicholas.
Nicholas, I'm sorry, Nicholas. I suppose it's 238, Nicholas?
Yes, sir.
That was a yes? 238?
Yes. Yes.
Oh, okay. Yeah. All right. Okay, now the secret to this class, Nicholas and the rest of you, are these PV diagrams. Nicholas wants me to do 238, and I don't mind doing it. But you've got to get your PV diagram. Now this is R410A. It's a hydrocarbon refrigerant. It's at 60 degrees, and it's saturated vapor. Now we know what saturated vapor is. That means it's on this line here. We are someplace on the saturated vapor line. Well, let me find R410A. Back in the back. Now, do we want metric or English? Well, if you got 60 degrees Celsius, Celsius is metric, you know what? So we don't want English. We want metric. So go to the metric tables. And I always go to the vapor dome table first. I found it. They call it the saturated table. We're going to find 60. Now 60 is towards the top of the vapor dome. It's at the bottom of the table. So that means it's at the top of the vapor dome. Here's your 60. There's your 60 degrees Celsius. And since it's saturated vapor, there's your state one right there. There's state one right there. You could write down a lot of information on that. Let me find it here. Now here's the pressure. The pressure is 36.9. Kilopascal. We can get the specific volume at 1. It's going to be equal to VG. See, VG is over on the right side, VF is on the left side. Well, VG is 0.00497. So we got the pressure, we got the temperature, we got the specific volume. And we're going to learn about the other things, the specific internal energy and the enthalpy and the entropy, but we don't know about them much yet. We'll get there. Let's read and see what they want us to do. Oh, they're going to decrease the pressure to increase the volume by 10%. Okay, well, we're going to increase this by 10%. Now, one way to do that is just to multiply, if you want the volume at state 2, multiply your volume at state 1 by 1.1. Now, that's how you increase something by 10%. Okay, so let me do that. I'm going to take 0.00497 and I'm going to multiply by 1.1, and here's what I get. I get 0.05467. We now know the specific volume at state 2. They've said we're going to keep the temperature constant. So we're going to go down here someplace to state 2. And we know what the new specific volume is. We also know the temperature. And we're going to find the pressure. I think that's what they wanted, right? Yeah. They want to know what this pressure is at 2. Come over here. That's going to be the pressure at 2. You want to know what it is. Well, see, we're in the superheated vapor region. So we're going to go to the superheated vapor chart. We know our pressure is less than 3,800. So we could try some of these. How about 3,000? Let's try that. At 3,000 kilopascals and a temperature of 60 degrees Celsius, the specific volume is 0.00858 cubic meters per kilogram. Now I got that on table B4.2. B.4.2. And Nicholas, are you able to pull up your table and see if you can find that 0.00858 for me? I need somebody to verify that.
Yes.
Yeah. Was that Nicholas?
No, this is Bryce, but
Yeah,
it is on the
it,
table.
right, Bryce?
Correct.
You
yes.
found it.
I
Good
found
going.
it too. Mhm.
Yeah, good going. Now, who was that?
That was Nicholas.
That was Nicholas. Okay.
I was
Good.
flipping to it. Yeah.
All right. Well, we want the pressure. Now, if you'll notice, 0.005 is in between 0.004 and 0.008. We're going to have to interpolate. See, at 36.9 kilopascals, we have a specific volume of 0.0497 cubic meters per kilogram. What we want is 0.00547. Well, see, that's in between 5 is in between 4 and 8. And so the pressure we want is in between these pressures. Does that make any sense?
Yes.
Well, we're just going to interpolate it now. Now I'm going to shut up for a minute and a half. And then I want to see if you can interpolate and get that pressure. That should be the answer that they wanted. I might even have, well, I didn't bring my answer book here. Maybe I have it here. But I'm going to shut up and I want you to do that, and then we'll see what we think. Well, I've got what I think is the pressure. I interpolated that. And what I got was 37.22 kilopascal. Does anybody need me to write that out, or are you okay?
Yes, if you could write it out real quick.
Okay, yeah, I'll be glad to. I'll write it out. Here goes. Need a little room here someplace. There's enough room right here, I think. Now what I'm going to do is I'm going to subtract these. And then I'm going to divide. See, what I did was I subtracted those. Now I'm going to divide by the difference between the whole thing there, which is point. And when I get all through there, I'm going to multiply that. What that is, it's a percentage. It turns out this is 86%. In other words, to get from here to here, I've got to go 86% of the way from here to here. Because this is 86% of the way from here to here. Okay, so what I have to do is I have to multiply this by and then when I'm all through with that, I have to add 3,000 to it. Now, if you'll do all that, you should get the pressure at state 2. We think it's 3722 kilopascals. Anybody getting that okay? Did that help any?
Yes, sir.
Yes.
Good. That's the answer.
Yeah, I understand now. Thank you.
Wonderful. Excellent. Okay, well, let's do some of this compressibility stuff. All right, now is there anything else? Anybody else? Okay, well, we're going to do problem 2, 116E together. It's an English one. We have to erase all this. You know what we never did? We never did the device sketch. We're going to do that in a minute, but here, let's do the device sketch. There's state 1. Here's state 2. Now, state 1 has higher pressure. And state 2 has lower pressure. See, if you take that weight off, does it make sense that if you remove that weight, your volume gets bigger? Kind of makes sense. Yeah. Well, look, the volume gets bigger. Going from 1 to 2, you're increasing your volume. What about the pressure? Well, if you take that weight off, the pressure goes down. Look, going from 1 to 2, the pressure went down, didn't it? Now, we stayed at a constant temperature. How would you do that? Well, you'd fill your bathtub up to 60 degrees Celsius. Man, I think that would roast you. That's awfully hot. And then what you do is you stick your piston cylinder in your bathtub there, and it would stay. Keep it in the bathtub. So if it's in a great big bathtub at 60 degrees, it doesn't matter. You can take that weight off, and that ain't gonna make it any hotter or colder. I tell you what it would do. If you didn't have it in the bathtub and you took that weight off, it gets colder. See, the opposite is when you compress a gas, it gets hot. You know that. Well, if you take the weight off, you're not compressing it, you're expanding it. Did you know when you expand it, it will get colder? Now, the reason why this doesn't get colder is it's in this warm bathtub, and there's a heat transfer going in. Now, we're very interested in the heat transfer because those cost money. And we'll study that later but I wanted to do your device sketch. I just did. Now you could label this with all the stuff here. You could label it with your temperatures and pressures and specific volumes. Temperatures, pressure, specific volume. There's your device sketches. Okay, I'm going to erase all this now. And then we're going to do 2116E. Here goes. That was for my friend Nick. Nicholas, did you understand what we did?
Yeah, I got it.
Oh, good. Keep going. See, I do the same doggone thing over and over. I do a PV diagram. No, PV diagram. Device sketch. Yeah, that's how you do these problems. Okay, now right now we're looking at 2116E. And let me find it now. Okay, I found it. Now this is ethane. Now we do not have an ethane table. You know, like for instance, we have water, we have ammonia, and we have refrigerants. We have a lot of tables in the back, but we do not have an ethane table. So you can't look it up in a table you don't have, but I tell you what we can do. We can go PV equals RT. We can do that. Now, what are we supposed to do in this problem? Let me read it. 2116E. Oh, they want the mass stored in a, and let me write some of this down. They said the volume is 25 cubic feet. And the temperature is 250 Fahrenheit. And the pressure is 440 PSI. Now see, a PSI stands for pound force per square inch. That's what a PSI is. Okay, now ethane, I'll tell you what ethane is. It's a hydrocarbon. It's got 2 carbons and 6 hydrogens. That's it. Here's the structural, here's the chemical formula for ethane. Now we're going to have to look up the gas constant. One way of doing it would be, oh gee, I don't have the English universal gas constant memorized. Is it 386? Don't know. We're going to look it up though. Go to the back and help me find the gas constant for ethane. And I'm trying to find it now. Ethane. There it is. No, it's 5138. Foot-pounds force per pound mass Rankine. I'm on table F.4. On table F.4, I looked up the gas constant for ethane. There it is. Okay. You know what? I think we might be better off to use. Let's use P big V equals M RT. That'd be okay. Let's do that. There's nothing wrong with doing it this way. It's just that if you do it that way, to find the mass, you're going to have to take the volume and divide by the specific volume. That'd be okay, but we'll just use this one. All right. Well, I think we know a lot of this stuff. We know the pressure. It's 440. Here, let me write it. I have room over here, 440 pounds force per square inch. Okay. Is that? It's off. It's off my screen. I don't know about your screen. Here, let me write it here. 440 pounds force per square inch. Okay. Yeah. Times the volume. Well, the volume's 25 cubic feet. There's an equal sign. Need a little room here. There's your unknown. We're going to solve for the mass. The R is 51, 38. And the temperature. Roughly, you have to add 460 to get Rankine. Roughly, it's 710 Rankine. It's really 459.67. But that's okay. We'll never know the difference. I just use 460. Okay, now here's the catch. You got to multiply this by 144 inches squared per square feet. And what that'll give you is, it will give you foot-pounds per pound mass. Wait a minute. No, it'll just give you foot-pounds. If you multiply by 144, this will give you foot-pounds. Now here over on the right, see, this will be pound mass. They cancel. The Rankines cancel. And you'll have foot-pounds on the right. So you'll have foot-pounds on the left and foot-pounds on the right. You won't have that unless you multiply by the 144. Okay, well, let's solve for our M now. Here goes. Get your calculators. And I'm going to do it. I want you to do it. Let's see if we get the same thing. I got an answer. Let me go to one of my wonderful students here. Let's go to my friend William. Unmute, William, and tell me what you got for the mass.
I'm still trying to find my calculator currently.
That's okay, William. Search around, maybe you'll find it. Look under the couch or under one of the cushions. Let's go to my friend Reagan. Reagan, have you got the mass yet?
No, I'm still calculating now.
You still working on it?
Yes, I'm still working on it, sir.
Well, that's fine. No problema. Let's go to my friend Nicholas. Go ahead.
This is Dawson. I got 43.4.
That's what I got, Austin. I got 43.4 2 on mass. Yay, we did that. We found the mass. Now, wait a minute. They want us to use compressibility. Now, you see, we found the mass using the ideal gas law, which is fine. That was fine. But they want us to use compressibility. So let's do it the way they want it. Here goes. Let's show you how to do that. Now we're going to get a better answer. Do you understand? The answer is going to be better now. But to use compressibility, you have to find the reduced pressure, which is your pressure, which is 440 psi divided by the critical pressure. What that is, that's the pressure at the top of the vapor dome. So go with me to, we got to find what the critical pressure is of ethane. And it's on page, I'm trying to find it. Yeah, here we go. Ethane. Critical pressure for ethane is 708 psi.
What were you looking at to get that?
Thank you for asking. Table F.1.
Thank you.
Go to table F.1 and look up ethane. Now we're going to need the reduced temperature. Now the reduced temperature is going to be the 710 Rankine divided by 549.7. Rankine. Okay. Now let's get those, and then we'll get our compressibility. All right, let me do that. I'm getting 0.62. And 1.3. Now, once you get that, we're going to go to that graph. And we're going to look up 0.62. And we're going to look up 1.3. Now 1.3 on this graph, it's in a figure D.1. We're going to look at figure D.1. And the 1.3 is a line that does this. It kind of comes down and goes over like that. And the 0.62 is down here. .62. I think that this actually has a more of a steeper slope. The 0.62 is you come up here, and then you come over here, and you can get your Z. Now I'm going to do that. I'm going to come up here, and I'm going to go to the 1.3. There it is. You know what? It's awfully close. The Z is awfully close to 0.9. Can you guys do that? I'm gonna wait a minute and let you guys stare at that graph there. It's figure D1. See, this is the 1.3 TR line, and this is the 0.62 reduced pressure line. Actually, these are dashed. These are solid here. That 1.3 is kind of solid. And then when you come over here, the Z is 0.9. I'll wait till you got to take a look at that. And then we're going to use the compressibility to find the mass. Now we found the mass, but this will not be the most accurate. With compressibility will be more accurate. Okay, now to do that, I need a little room. I'm going to have to erase some stuff to make room for this. Here we go. Now what we're going to do is we're going to go PV, that's a big V now, equals Z MRT. But we know what Z is. In fact, we know what all this stuff is. We know we have to have a 144, and we know the pressure is 440. I've got the units all right here. The Z is 0.9, and the R is 710. No. The R is 51.38, and the temperature is 710. Now, I was lazy and I didn't write in my units, but I've got my units right here. They're right there. So I can get away with that this time. Okay, now we're going to solve for the M, and this will be more accurate. Okay, here goes. I'm plugging that in now.
I have a question, Professor Griffin.
Yeah, go ahead.
When you wrote those down, did you forget to put the volume? Because you have 144 and then 4.
I did. You're absolutely, this is wrong. Now, who was that just spoke up?
No, I think that one's right, but the one that you're calculating now is the one without
Oh, yeah, I did put the volume on that. There it is, but I forgot it here. I'm going to give you a honking thank you point, but who am I talking to?
This is Dawson.
Dawson, thank you, Dawson. There needs to be a 25 in here, huh, Dawson?
Yeah.
Right in here, right?
Correct.
Yeah, good going, Dawson. Okay, now let me do this right. I'm trying to do this right now. Now I'm getting an answer this time of 48.25 pounds mass. We'll put a little happy face on that. That's more accurate than the 43 pounds mass, because we use a more accurate model. See, compressibility is a more accurate model. Now, if we had a table, it would be even more accurate. But I'm going to wait till I hear a couple more uh-huhs on that 48.
Yeah.
Uh-huh.
Yeah, I heard one there. Okay. Well, let's do one that has a table. See, the tables are the most accurate. Oh, if you read this problem, we just did problem 2, 116E. They wanted to know the percent error. Well, assuming that this is correct, if you wanted the percent error, we'll make some room right in here. To get the percent error, you would take the 48.25, subtract the 43.42, divide by the 48.25, because that's the most accurate, multiply by 100, and the book answer says 10%. I looked up the answer. Do that and let's see if that's what we get. 48.25 minus 43.42 divided by 48.25. Boy, Jove, you get 10%. So we were able to improve our accuracy by 10%. So that was fun. Any comments or questions on problem 2, 116E?
Mr. Griffin,
Yes.
that value of z can be like maybe a little bit up or down when we're seeing the graph, or it has to be like exact 0.9.
Oh, if you read 0.91 or 0.88, it's hard to read a graph. Don't worry about that. Okay.
That's fine.
You're fine.
Okay.
Because it's just not exact. Graphing is just not the most accurate thing in the world. Okay, well let's try another one. Okay, this one we're going to do methane. I need a little room here. We'll say goodbye to ethane. And now we're going to do methane. Now, I think we do have a methane table. Now, this is not in your book. This is just a problem. This is a problem I took off of an exam I gave in 2013, 7 years ago. The students that took this problem, a lot of them are out there making more money than I am now, with good jobs, which makes me very happy. Now we're talking about methane, and let me tell you what we have here. We have methane, and that's CH4. and it's at 290.4 Kelvin and 4,000 kilopascal. Okay. Wait a minute. No, it's 4,600. It looks like 4,600 kilopascals. All right. And the volume is 8 cubic meters. Okay, now the first thing we're going to do is we're going to find the specific volume from the methane table. Go to the back and help me find the methane table. Methane. And help me shop around here. Let's see. There's water. And carbon dioxide. R410A. I'm looking for methane. Nitrogen. Methane. Ta-da! I found it. Methane. Now we need the specific volume if you know the temperature. Now, how do you go about doing that? Well, I guess you could draw your PV diagram to see where you are. Let's do that. I like to know where I'm at. Now I'm looking at table B.7. And we want 490.4 K. Well, where is that? Oh, gee. That's up above the vapor dome, you know it? That's way the heck up here someplace. It's not in the vapor dome. 490. No, not 490. 290. Did I say something wrong? Yeah. Yeah, 290. 290.4 K is above the vapor dome because it only goes up to 190.6. Look on table B.7. See, the peak, the top of the hill there is 190 and we got 290. Okay. And what about our pressure? Well, they have 4,600. That's right at the top of the vapor dome, but it's right about here. Right about there. Pretty even with the top of the vapor dome. Okay. There's your state. You can call it 1 if you want, but we're not going anyplace. We're just going to look it up. But see, it's superheated vapor. So go to the superheated vapor chart. What we want is what, 4,600? Oh, gee, they don't have a 4,600. Well, that's kind of a problem. Tell you what, let's make this problem easier, all right? Instead of having 4,600, let's just have it 4,000. 4,000, because see, that's in the back of the table. I just want to make this as easy as possible for us. We're still going to have to interpolate, though, I think. We got 4,000 kilopascals. And we need the specific volume. Well, here's what they said in the back. And they said, I'm on table B7.2. at 4,000 kilopascals and 186.10 K, they said the specific volume is 0.01160. See if you can find that in the back. But see, that's 186K. Now what we got is 290. No, never mind. Never mind that. We don't need that. I goofed up. What we need is at 275K, specific volume is 0.03235. And at 300K, specific volume is 0.03631. Table B.7.2, methane, 4,000 kilopascals. But what we want is 290.4K. Well, we can get it. It's just a matter of interpolating between these two numbers. I know we can do it. And we'll have the best answer. I'm going to be quiet now for a minute, and I want you to interpolate that. Go for it. And I'm going to do it. And we'll see if we can agree here. Well, I finally think I got the, I think I've got it. I'm getting 0.03479. Wonder if that's right.
That's what I got.
Hey, I'm glad to hear it. Okay, now that's the best answer. Here, let's put a little table over here. Specific volume using the tables is 0.03479. Is there room for me to write cubic meters per kilogram there, barely? Yeah. Okay, we did the tables, yay. Now let's do the ideal gas. Here we go. I need this room. Say goodbye to all this because we're just going to use the ideal gas law now. And now you can put a happy face on this one. That's the best answer that we will have. But now if you use the ideal gas law, we're going to go PV equals RT. All right. We're going to have to look up the gas constant for methane. Help me look that up. Start shopping around. Help me find the gas constant for methane. I'm getting 0.5183. Kilojoules per kilogram Kelvin. Now we already have Kelvin, so it's 290.4 Kelvin. And we have the pressure, it's 4,000. Do I need to help anybody find the 0.5183 for methane? It's table 8.5. But if you're happy with that, we can find the specific volume using the ideal gas law. Here goes. I'm getting 0.0376. It's off quite a bit. See, the correct answer is 0.3. Well, they would round off to 0.35, and that would round off to 0.38. So we're off quite a bit. This does not get a happy face. But we use the ideal gas law, and it's not as good as the tables. Did anybody get that?
Yes, sir.
Great. Now we're going to do it with the compressibility. Now we should get a better answer with the compressibility. So here, let's do that. I just wonder where I'm going to do it. I'll leave that up there for a minute, and I'll just erase all that, and we'll do it with compressibility. Now you need to know something. If you have a table, use the table. Don't use the ideal gas law, and don't use compressibility. Use the table. If you don't have a table, well, you can't use the table if you don't have one. You're pretty much forced to use ideal gas law or compressibility. You can't use a table if you don't have one. Okay, I'm going to make some room now. And we're going to do it with the ideal gas law, or I mean with the compressibility. Here goes. Well, we have to go through this little dance that we go through. We got to get the PR and the TR. Well, the pressure is 4,000 kilopascals. And we're dealing with methane. And methane trying to find it. And I finally found it. It's so you take your pressure, which is 4 point, we'll do it in megapascals, and you divide by 4.6. Now I found that on table 8.2. And now we're going to get the reduced temperature. The reduced temperature will be 290.4 Kelvin divided by, it looks like 190.4. I got that from table A2. Okay, great. All right, let's get those values. Here we go. This will be 0.87 maybe, close to 0.9, and this will be I think I'll just round it off to 1.5. That's good enough. Now to find the Z, here we go. We're going to find the compressibility because see what we're going to use is PV equals ZRT. And we know what the pressure is. We know the Z, we're going to find the Z. What's the R? I lost the R. I hope somebody knows what that is because I lost it. But anyway, go to help me find the Z here on this graph. And we need a 0.87. All right, I can find that. Gee, that's awfully close to 0.9. And then you go up to 1.5. Okay, there's one. Wow, that's way up high, 1.5. You know what? It's about 0.92, maybe 0.91. And Z is about 0.91, maybe 0.92. And like Mohammed was asking me, well, what if you got 0.92? Well, yeah, that's just as good as mine. I'm just guessing. It's hard to read a graph. Now let's write it out. Here we go. We're going to write this out. The pressure is 4,000. We're going to solve for the volume. Z is I got 0.91. Now the R, I got lost there. Let me see if I can find the R for methane. I got lost.
I think we had, might be wrong, but 0.5183.
Thank you so very much. I'm
Yeah,
sure
that's
that's right. And then the temperature is 290.4. I had all the units on there before, so I'm being a little bit lazy. Now we're going to solve that and we're going to get the value of the specific volume using compressibility. Here goes. Plug all that in. Here goes. And thanks for your help. Okay, I'm getting a 0.0342 cubic meters per kilogram. Now, this is the correct answer. This is the answer using compressibility. Gee, it's not too terribly bad. It's off a little bit. But now I forgot what the answer was with the ideal gas law. What was the answer with the ideal gas law? Does anybody? I think I erased it.
It was 0.0376 with the sad face.
Yeah. Now, guys, can you see that this here? We'll put a little happy face on there. It's a whole lot better than the 0.037. That's way off. This is the correct answer from the tables. That's the best model. This is the second best model. It's off a little bit, but not too terribly bad. And the ideal gas law is off quite a bit. You could figure the percentage it's off. But let me show you something that maybe will explain all this. If I can find it here. I'm shopping around here. I wanted to show you something. And then it'd be fun. Oh gosh, our time just slips away. Now, here's what I want to show you. I need some room here to show you this. In your book on page 50, they have a graph, and on this graph, you know what it is? It's a TV graph. Now you guys are used to PV graphs, but TV graphs are pretty similar. And then they have this, it's interesting, they have this region here. And they said that anything in here, the error is less than 1%. What they're saying is, if you got a low enough, of course, I know that's a temperature graph, but you could draw a PV graph and it would look very similar. Just pretend that's a PV graph because it would look very similar. Down here, if the pressure is low enough, what they're telling you is the ideal gas law will give you the same answer as the tables if the pressure is low enough. Now, as the pressure gets higher, the error gets bigger. See, error in here, anything in here, the error is bigger. It's certainly bigger than 1%. It might be, who knows, 10% or something like that. Now, there's two ways you can get lucky with the ideal gas law if the pressure is low enough. Now the reason, the other way is if it's hot enough. See, the reason why you run into problems with things like H2O, for instance. H2O is a bipolar molecule. It has a positive and it has a negative polarity. And if you get two water molecules together, just right, if they collide, if enough of them collide, you got yourself a water drop. You are no longer a vapor, you are a liquid. And the same is true with all these others like methane or ethane or your refrigerants. If those molecules get close enough, how do you get them close? Well, at high pressure. See the pressure here? If you get the pressure high enough, they slam into each other and they form droplets. And you're no longer a vapor anymore. You got some liquid. So that's kind of an interesting graph there. I never have talked to you about TV graphs. But just remember, if the pressure is low enough, see that thins the molecules out. At very low pressures, all gases behave like ideal gases. Here, let me write that for you. I might have told you that, but I don't remember what I tell you. All gases behave like ideal gases if the pressure is low enough. Because the reason for that is the density is low enough. If the density is very low, if you can spread the molecules apart, they don't run into each other and they don't start forming droplets, okay? All gases, let's put in the word behave. All gases behave like ideal gases if the density is low enough. As the density, if you pack them in there, if the density gets higher and they start running into each other, you're running into a saturated mixture now. You're running into liquid because they start glomming onto each other and forming raindrops or whatever. Then the other statement that I might have made to you guys is that there are no ideal gases. There are no ideal gases. I guess the word we should put in here is perfectly. We can get close, but there are no perfect ideal gases. The best one we have is helium. Helium really behaves nice. But even helium can be liquefied. Did you know that? You can have liquid helium. And of course, once it's liquid, well, you can't use the ideal gas law on a liquid. But at normal temperatures and pressures, helium acts like an ideal gas. But the rule is, if you're going to be really nitpicky, there is no perfectly ideal gas out there. There is none. Except all gases will behave like ideal gases if you can thin them out enough. Okay, well, there's that. And you've got your homework for me. We have a few minutes left, but I don't have enough time to do another problem. Did you have a comment or question for me? Anyone?
Do most problems, they'll state if the density is low enough so that we can utilize the ideal gas law?
Excellent question. And now who am I talking to?
This is Bryce.
Bryce, thanks for asking, Bryce. Now here's how you do that. You find the decompressibility. Now, this is really kind of a rule of thumb, but obviously if you come out with Z is 0.99, I would just say use the ideal gas law. That's awfully close to 1, isn't it? See, PV equals 0.99 RT. You could just call that a 1 and forget it. And you got yourself an ideal gas law. In fact, ask yourself, how accurately can you measure temperature and pressure? Like if you take your kid's temperature, what's it supposed to be? 98.6 is the normal one. But we're all different. Some of us consistently have a lower temperature, which you could be off by maybe, I don't know, it could be 98.3, and they'd still let you in the building. You know, with the COVID thing, you could even be 99.0, and I think they'll let you in the building. But now if you're 103, they'll say, no, can't come in. You got a temperature. But just how accurate can you measure these things? Well, the truth is, thermometers and pressure gauges, I don't know, you might be able to get 3% accuracy when you measure pressures and temperatures. So to answer, I think it was Bryce that asked me, Bryce, if you come out with 0.97, go with the ideal gas law. If it comes out lower than that, then you're not dealing with an ideal gas. It's just not perfect. What do you do then? Well, if you have a table, you use the table. What if you don't have a table? Well, then you use a compressibility. Was that Bryce? And did I answer your question okay, Bryce?
Yes.
Anybody else? Yeah, see, we have a way of knowing whether we're dealing with an ideal gas or not. You can find the Z. Well, okay, that was fun. And you've got homework to do. And I will see you next Tuesday at 11, right? That's the next meeting. And I will, am I supposed to post anything on Blackboard? I don't think so. You have homework. If I think I'll sign off, guys. It's been fun. See you next time. Bye-bye.
Thank you.
Thank you.